All right, welcome to today's class of CSC 365. Again, we are continuing to go over the intercepting communication module, in which we're discussing a whole bunch of concepts surrounding network security. Before we get started, are there any general questions about the class? Nope. Okay. Are there any general questions about the module? All right, we'll take that as a no. All right, then before we let's jump into the challenges. So are there questions surrounding, let's say, the first 10 levels that people have? Yeah, question about the first 10 levels? Level 9 and 10? Okay, let's take a look at level 9. Do you have a specific question about level 9 and 10 that's coming up? You don't? Okay, yeah. Let's look at what it's asking for and try and explain it a little bit better. Okay, so level 9. We run the challenge. It tells us, in this challenge, you will manually send an internet protocol packet. So level 8 has you sending an Ethernet packet. Level 9 has you sending an internet protocol packet. The packet should have IP proto equals 0xFF. The packet should be sent to the remote host at 10.0.0.3. Actually, before I begin demonstrating this, let me switch into practice mode so that if we want to take a look at the network traffic easily, we can for explanation purposes. Okay. Challenge baby intercepts sudo. Okay, so if we run it this way in practice mode, run the challenge with sudo, we're going to get a network dump of all of the traffic going on. So we run this, and now we look at temp pcaps. We can see we have these two hosts on the network that are generating traffic. We have ourselves, 10.0.0.2, and our person we're going to get ready to communicate by manually sending a packet to 10.0.0.3, and we're getting network dumps of all of the traffic. So we can just kind of investigate, for example, what kind of traffic is going through our interface. So specifically, what kind of traffic is going through our ETH0 interface here, and then also what is going through 10.0.0.3's ETH0 interface. I guess one thing to point out in the case of these challenges is that we don't actually have an IP address assigned to ourselves. If we take a look at this interface, we can see there's no IP address assigned. For these manually sending packet challenges, we don't assign an IP address, basically because we don't want the kernel to just start automatically doing stuff, since it's a very manual all of these challenges in this area of the module are surrounding manually sending packets. We don't want packets accidentally being sent, basically, which is why. But you can basically think of it enough that you have 10.0.0.2. It's just the kernel is not going to be responding on your behalf for some things. Okay, anyways. So we want to send a packet with IP proto equals 0xFF. The packet should be sent to the remote host at 10.0.0.3. So if we want to investigate this network traffic, we can either use TCP dump or we can use Wireshark. I'm just going to jump straight into Wireshark. So if we do Wireshark temp pcaps IP 10.0.0.2.pcap, it's going to show us all of the traffic. You can kind of ignore all of this. This is like some IPv6 stuff that's just automatically happening. Basically, we have no traffic. Similarly, if we look at 10.0.0.3, what's going on its network, it has basically nothing going on as well. You can kind of ignore this ICPM v6 stuff. This is like IPv6 stuff that it's automatically happening. We don't cover IPv6 stuff, at least in this module, or really any future module. Maybe eventually in a future class there'll be IPv6 stuff, but we can ignore this traffic. Okay, so no traffic is happening, which makes sense because this challenge isn't telling us that there's like a service running and people are communicating or anything like that. It's just telling us we want to send this packet manually. So what we can do in order to investigate this, and actually it'll probably be a little bit easier to view this rather than using Wireshark, let's go ahead and use TCP dump so that we can view everything happening. So we're going to have 3 windows. So we can see at the very bottom, we have 3 tmux windows. We've got 0, 1, and 2. On 1, we're going to do TCP dump this command, basically to read from that pcap file, IP 10.0.0.2 .pcap. And if we do this, we can see all that traffic that we saw in Wireshark. Instead, though, let's do, how do we want to show this? Let's instead read from standard in and do what we kind of showed in the last lecture, where we can tail temp pcap's IP 10.0.0.2 pcap, pipe that into TCP dump. So basically now we're reading from standard input. Tail is going to give us the end of this. That's kind of what tail does by default. If we do man tail, output the last part of the file. We also have this -f thing, which can output appended data as the file grows. So it'll just keep adding data, which makes sense because we're going to be continuously gaining network traffic showing up in this pcap file. So we're going to follow this. And then also, rather than just showing the end, we want to show everything. So if we do -c, I think C0 is good enough. We can see, maybe not. Hold on, let's see. Does that actually matter? Does. Okay. -c plus 0. And we can just basically see traffic as it comes in. Similarly, we're going to do the same thing in this other tmux window, but for 3. Okay. This basically is going to enable us to just see traffic as it happens. And then one more thing we're going to do is, while true, we're going to do this because every once in a while, every minute, these pcaps are going to get deleted and then reset up, basically, so that these files don't just get massive in some circumstances. So we're just going to continuously do this. Okay. And then, well, true, do that, and done. Okay. Cool. So now we've got this, we've got this. So we've got basically the ability to view all of our traffic as it's coming in. Okay, so now we want to manually send out traffic. So if we want to send out, for example, an Ethernet packet, we can create an Ethernet packet like this, right? And if we do send P, this is going to send that packet. And we want to specify ETH0 to say, hey, we want to send this packet on the ETH0 interface. So if we do this, we're going to see that this loopback invalid thing is that packet we just sent. And basically, we can see that showing up on our interface, but it's not reaching 10.0.0.3. It's only going through our interface, and it's not being delivered to 10.0.0.3. On the other hand, if we do, actually I'm going to make this even more clear. We're going to add this -XX thing to just like show the raw bytes also of these packets. Cool. All right, so now if we send that right, we can see this packet automatically going out right here. If we look at this Ethernet packet and do show, we can see that it has a destination address of FFFFF, source of all zeros, and type of hex 9000. And if we look at that right, we can see that that's exactly how this is being sent according to how this packet gets laid out, which of course is explained in this video that kind of shows the exact structure of this packet, right? We've got these 14 bytes. Okay. So, and then I guess one more thing we can show is instead of .show, we can call like bytes on this thing. And that's just going to print us these 14 raw bytes, right? This kind of lines up. Just one more way of visualizing that. Okay, on the other hand, and we can also note that none of these packets are reaching 10.0.0.3, even though we're sending it on the broadcast address for whatever reason. And honestly, I'm not entirely sure what the factor is that's preventing it from being reached, because we are sending this out on this broadcast address. But something is preventing this packet from going out. If, on the other hand, we set our source to be our MAC address, if we say source equals get if, actually, let's show that first. Get if hardware adder, which is a function with SCAPI that gives us our MAC address. You can also look IPA, right? We've got this value right here. This lines up. So this is our ETH0's MAC address. If we get ready to send a packet with that as our source, equals get if hardware adder ETH0, and we send that, right? We can see this packet just came out across the wire, right, with this updated MAC address here. And also, we can see now it is showing up on 10.0.0.3. So clearly there's this importance of kind of correctly specifying our source MAC address. So this is an Ethernet packet. We want to send an IP packet, though. So how do we make an IP packet? Well, if we call IP, to create this object, we have just constructed an IP packet. Again, we haven't sent this out. We don't see this showing up on the network anywhere. But we have created this object. And similarly, we can do something like source equals 10.0.0.2, destination equals 10.0.0.3. Again, this doesn't just automatically send that packet out, never went. But this is how we can construct this. Now, if we wanted to send this, we could, for example, do send p and say iface equals eth0. And if we do this, we're going to see, let's send that again. We're going to see that it is not showing up anywhere. Is that true? Hold on. Actually, it is showing up. That's interesting. Interesting. I was going to say that it's probably not showing up, but it is showing up. Okay, Scapy is very intelligent. It must be automatically constructing. Hold on, let's see here. If we do, one way to view this is if we do 255, 255, 255, 255, and then we could do, let's say, 128, 128, 128. We look at this. We can see this is that 255, 255, 255 part of this IP packet. This is the 128, 128, 128 converted to hex, and this is also showing up. So interesting. Okay, I was going to say that Scapy isn't going to send this. Turns out Scapy is very intelligent and is automatically putting an Ethernet frame underneath it. So, in fact, I wonder if we were to specify proto equals hex 42. We can see that 42 right here that we just put in. 42 right here. So it looks like we could actually do this. If we wanted to be a little more correct, because I'm not totally sure how this is functioning, if we wanted to be a little more correct, we would put an Ethernet frame under it. So what that would look like, again, is to do ether/IP. So this creates an Ethernet packet with an IP packet inside of it. And if we do .show on this thing, we can see we have this Ethernet packet with all of these Fs, all of these zeros, a type of IPv4, and then a bunch of IP info. Again, if we do bytes of this thing, we can see all of the bytes that would look like. And if we do similarly to setting up our, actually we won't do that initially. We can do, let's just say proto equals hex 42, right, to construct this thing with a hex 42 prototype on this IP address. If you're confused what this prototype thing is, watch this video. And then more specifically, this video, which would show what a prototype would be for TCP, right? So if we have this IP packet, we have 1 byte specifying the protocol. For TCP that's going to then live on top of IP, we would specify a prototype of 06, and then that would say that, hey, the following data is going to be a TCP packet. That's what that proto is doing. Okay, but in this case, if we just randomly say hex 42, and we get ready to send this packet with iface equals eth0, we can see we have all these Fs, all these zeros. This says, hey, this is going to be an IPv4 packet. Well, this says it's going to be an IP packet. This says it's IPv4. And then somewhere in here, this 42 appears. This 42 right here, which is the prototype we specified. On the other hand, if we say it equals hex 77, right, we're going to see we've got this packet that just went through the network, and here is our hex 77 that we just specified right here. However, these packets are not showing up on 10.0.0.3's network traffic, right? We don't see any of these packets that we're sending. If we do like while true, how do I want to do this actually? While true, import time. while true, do this, and then sleep time dot sleep 1, right? So this is just every second going to send out another packet. We can see these packets showing up here constantly, but again, they are not showing up here. It's nowhere to be found. The reason for that, even though this is going on a broadcast MAC address, the reason for that is we need to specify a source of get if hardware adder eth0, specify our source. So now we've got our source MAC address being filled in here, right? We can see right up in here is our source MAC address. And now this traffic is showing up on 10.0.0.3 as well. Okay, so one more thing is obviously we don't want a prototype of 77, but I assure you, right, you said it's a FF, it's going to be good to go. If we wanted to make this a little more correct, right, we're kind of doing the bare minimum. And actually, hold on. Let me see what the challenge is actually requiring. It might be requiring you to do something a little bit more. Yeah, so it actually is requiring you to be more specifically correct, because as the challenge says, it wants its destination IP address, right? We're trying to send a packet, an IP packet to 10.0.0.3, which means that you want to actually specify this IP address in this IP address, or within this IP packet. So it's not required in order for this packet to actually physically show up on its network. It's just incorrect from the sense of if we're going to 10.0.0.3, we need to specify that the IP address is 10.0.0.3. Otherwise, it's not really going to 10.0.0.3 under normal circumstances. If you had some server listening on some interface for IP traffic, and it says like, hey, we're listening on local hosts like 127.0.0.1, or we're listening on IP address 10.0.0.3. If you don't specify that destination IP address, the server is never going to get that packet at a higher level. So it is showing up on the network, on its perspective from the network. It's just no one would respond to that, which is why you do need to be correct here and specify this destination IP address. And probably even better, specify your source also. Like, let's just make this correct, right? We got a source IP address of 10.0.0.2, destination IP address of 10.0.0.3, and then some proto of, let's say, some proto of, let's say, in this case, we'll just do 77 so that the challenge doesn't get killed. And this is going to be every second we're seeing this packet get sent out. And again, we can see it over here, right? So now even Wireshark, actually, hold on, not Wireshark. Kill that real quick. So whereas before we could see this traffic just appeared as coming from localhost to localhost. The reason for that is that Scapy is automatically filling in 127.0.0.1. So right here, you can see this 7F, which is 127 decimal. And then this is 00, which is 0 decimal, 00, again, 0 decimal, 01. So this, by default, Scapy fills in a bunch of fields. So it's sending it from localhost to localhost. Whereas now, once we've correctly specified these IP addresses, we can see that TCP dump is actually showing us that, hey, it's going from 10.0.0.2 to 10.0.0.3. Again, this is just like basically made up. It's just TCP dump is reporting what it sees. So instead, we could be like 77.77.77.77. And similarly, we would see, right, that traffic is just showing up as coming from there. Even though that's not our IP address, it's reporting what it's seeing is the kind of the way to think about that. But ultimately, specify your destination. And then if we were to specify our prototype of FF, we would see the challenge gets killed because the packet has arrived now with the correct prototype going to the correct destination. And so as soon as the challenge detects that the correct packet has been sent out, it just kills the whole challenge and prints out the flag. So that is what happens there. Are there any more questions on how level 9 is working? Does that make sense? Yeah, okay. Any other questions on level 9 that anyone has, or anything specific to what I just did here? Because the same concept kind of goes on for a lot of the challenges in terms of just manually crafting a packet. Yeah, there's a question? Mine's a bit more specific to 10. Okay. It's the same thing basically, but you have to do a TCP packet on top of it as well. Yeah. And I put all
it's sending a packet.
Uh-huh.
It's not like
And have you run it with practice mode? Okay. So if you run it with practice mode, depending on what you're doing, we would see if that packet is showing up on the destination. But let's kind of show level 10. So if we do sudo challenge baby intercept with practice mode level 10, we are going to see that, as you said, it's kind of, wait, what just happened? What? I think I've ever seen this before. Let's try that one more time. Curious what happened there. Hold on. I can assume that just very rarely happens because I've never seen that before. That's interesting to know. I'll pay attention to that later. Okay, it's working correctly now. You ever see a random exception at the very beginning? Definitely report it in the Discord. I'm going to guess this happening here is super rare, but I will look at why that's happening later. Okay. It happened to you for 10? Yeah. Okay, well, I'm not sure. If it does happen, just restart the challenge until that doesn't happen, because it probably is an issue. But if the challenge does start in that way, it's probably a big issue in order to solve it. But just restart it until that doesn't happen. Hopefully it's rare-ish, but I'll investigate that. Okay, so level 10. Actually, let's run this challenge again so we can see the message. Okay. So it says the packet should have, or it says in this challenge, you will manually send a transmission control protocol packet. The packet should have TCP and all of these fields filled in. So it says source port 31337, destination port 31337, sequence 31337, acknowledgement 31337, and flags acknowledgement, push, reset, SYN, and finish. So just a bunch of flags. Under normal operation, you would never see a TCP packet that looks anything like this. Probably. It would be very weird if you did. But there's no reason we can't craft this packet. Okay, so if we start up the challenge with tmux again, actually, let me copy all of this so that we have it. Actually, copy all of that, run tmux, scapy. Cool. Okay, so we've just kind of saved that away so that we have that for, let's say, description equals that. Now we can just print the description whenever we want to see what we want to do. Print description. Cool. Okay, so then let's also set up TCP dump. We lost the history. TCP dump LR XX from standard input tail C plus 0 dash F temp pcaps. Pipe that in IP 10.0.0.2 pcap. Probably be cool to make this easier, but okay, anyways, so let's get ready to start printing out that. So this is our 10.0.0.2 traffic, everything coming across here. Cool, and then let's run that again, but for 10.0.0.3. And then one more thing. Wait, we forgot our while true. While true, do this. And then while true, do this. Cool. And then I guess one more thing, is that the only pcaps? Yes, there's only these two. So there's only two hosts on this network, us and someone else. Okay, so foreground. Okay, so we need to send a TCP packet with all of this. So again, if we want to get ready to build that packet, we could do TCP. And we can just fill in exactly as it tells us all of these fields. So it says you want a source port of 31337. We can say that. Similarly with all these other fields, dport equals 31337, sequence equals 31337, acknowledgements equals 31337, and finally we want flags equal to this. Scapy is just supposed to be super user friendly, so we can just like very directly say flags equals that as a string, and it's reorganized the direction of this. But again, these are just numbers, right? This is just a bit field. So if instead we print dot flags, right, we can see that that's 31 represents this. We print this as like a hex number. Can we not? We convert it to an int and then hex. We can see that it's just this number means all of these flags turned on. If we turn off, like, let's say if we turn off the sin part of the flags, we can see it's different. Actually, it's going to be a little bit easier to view this in binary. And if we turn off, let's just say this S part of the flag, right, we can see that this 1 turned into a 0, right? It's just a bit field. A bunch of bits represent all of these different flags. Okay, so this is the packet that we want to send out. So obviously the simplest thing to do would be to just do like send p iface equals eth0. And if we do this, it tells us no IP underlayer to compute checksum, leaving null. Something happened probably. Let's see what happened. So some packet went out right here. This looks like what we sent. So we can see it did send something out. And it looks like it actually is showing up on both. That's interesting. Scappy is super smart. Huh. Did not realize how intelligent Scappy was about just automatically filling in those underlayers. But anyways, let's see here. And just to demonstrate that this is all of these values, if we change, let's say the sequence number to be 0x4242, we can see right here that 4242 is this portion of the packet. It looks like this is showing up, but this is, I'm just going to say, not good. I don't even know because it's missing the, like it's just starting with the TCP portion. I don't know what this packet is. Let's see actually what Wireshark tells us, because I'm curious what this packet is, that it's like missing all of these under portions. So if we open this up with Wireshark, temp, pcaps, IP 10.0.0.2.pcap, it tells us that this is the packet that was sent. So it's like reinterpreting everything. So we can see that the way that this is being detected, like we're just sending out a TCP packet over the wire, and it's showing up over here, which is interesting. But this is just being interpreted as an Ethernet packet. So this 0 or this hex 4242 part of sequence is actually being considered part of the source MAC address, right? All we're doing is sending a bunch of bytes over the network, and I guess these bytes are valid enough even to show up on 10.0.0.3. But it's being interpreted as an Ethernet packet. It's not being interpreted as a TCP packet. So we want to set everything up correctly. And by that, I mean, let's put everything on top of its correct layers. So this is TCP. We want an IP packet underneath it, and we want an Ethernet packet underneath that. So if we do all of this, do .show, we can see that we have an Ethernet packet, and on top of that, we have an IP packet, and on top of that, we have a TCP packet. So this is what a normal, TCP packet going over IP, going over Ethernet looks like, right? We say Ethernet /IP /TCP, and we can fill in all the fields we want to fill in. So probably we're going to want to specify our source MAC address correctly. So get if hardware adder eth0. We'll just leave this as being broadcast to everyone. So probably under like traditional circumstances, we would send this to 10.0.0.3's MAC address as the destination MAC address. You don't have to do that. You can just broadcast it. It's a little weird, but normally you would specify a destination of 10.0.0.3's MAC address. And the way that you would get that, of course, is doing an ARP request, which you're going to be doing ARP in the next level, or is that true? Maybe in 2 levels from there. But that's fine. You can just broadcast this IP packet as well, and it'll show up to everyone on the host or everyone on the network. But normally you would specify 10.0.0.3's Ethernet MAC address. And then we want to fill in this source and destination because, again, we're not trying to send like from 127.0.0.1 to 127.0.0.1. We want we want to be talking to 10.0.0.3, and we are 10.0.0.2, so we would fill in all of that under the IP layer. So we would say IP source equals 10.0.0.2, destination equals 10.0.0.3 to be correct here. And now we filled in those portions. Scapy again is smart. It's automatically filled in a prototype of TCP because it knows TCP is about to live on top. So it does that for us. Similarly, it filled in IPv4 because it knows IP lives on top of this. So Scapy just kind of filled in these types for us. Right now, it's got these other important fields like checksum. And checksum, in this case, it says none. When checksums are none, basically right before Scapy goes to send the packet out, it will compute these checksums because, again, these checksums are important, and that's kind of like a hint for, I think, like level 14, for example. Something to think about is these checksums. They are important, but if they're set to none, Scapy will automatically compute them before the packet gets sent out because Scapy is super awesome about doing that. And then we've got all these flags on. So this looks approximately correct. And so the next thing that we would do to view this, actually, we would do send p, put this packet in there, oops, and say iface equals eth0. So we send this packet out, and if we look here, we can see that this crazy packet just showed up on our interface. So this is 10.0.0.2's interface. We can see that we have from 10.0.0.2, port 31337 to 10.0.0.3, port 31337. All of these flags turned on, this sequence number, this acknowledgement number. What else? It's not telling, oh no, it did tell us the source port, destination port. So it has all of this stuff that's showing up. And if we look over here, so if I'm now looking at 10.0.0.3's perspective, it can also see this packet showing up. So, I mean, the only thing missing now is to kind of specify the correct sequence number, right? We changed that to hex 4242. Again, we could change this to like 7777. If we look here, we can see that 7777 right there. We look at this in Wireshark. We can view everything as well. So this is our packet. We've got Ethernet, we've got IP, we've got TCP, we've got source port 31337, destination port 31337. This sequence number, this is our hex 7777 being converted. Oops. I do, for example, 0x7777, that is 3583, which is 3583 right here, the sequence number. And we can see all these flags turned on, etc. We can see all of this packet correctly filled out in Wireshark. We can see that that's showing up on 10.0.0.2's perspective. We can also see that's showing up on 10.0.0.3's perspective. It's critical that this packet is reaching where it's going. It's kind of like the first step is make sure the packet is arriving where it needs to be going as like a first troubleshooting technique. And if it's not, then you need to start looking at what you're sending. And it turns out one of the big errors that people are making is that they're A, not layering all of these things correctly, and B, not setting their source MAC address. I'm not totally sure why you need to specify your source MAC address for these packets to be delivered, but you definitely do. And then from there, it's just filling in everything that the challenge tells you to fill in, right? It's going to 10.0.0.3, 10.0.0.3, all of these fields, right? We've changed this sequence number. And then also make sure you're sending it over the eth0 interface. If you don't do that, it's going to go back over the loopback interface. And if you go over the loopback interface, it's not connected to the network, so it's never going to show up at 10.0.0.3. Because 10.0.0.3, that host is not connected to your loopback interface in some way. It's got to go over the eth0 interface in order to be, you can kind of think of it as being plugged into this like network device. It's got to be plugged in. And by plugged in, I mean like send it over the eth0 interface. That's the only way it has any chance of getting there, because that's how everything on the back end is like virtually wired up. It's got to go through this port. Okay, and then I guess just to show it, since it's so close anyways, if we change this to 31337, right, kills the challenge flag, pops out. Any more questions about levels 9 or 10, any of this like concept of sending out a packet? This is kind of, if it's not working, it's really important to learn these skills of troubleshooting network traffic. And the best way to do that is to use TCP dump and Wireshark at different points. And practice mode with sudo running the challenge allows you to introspect the network traffic and see packets showing up. You can use Wireshark, look to see that this packet is in fact showing up at 10.0.0.3, right? This is the 10.0.0.3 PCAP. And then once we know that it's showing up, we can see this packet, so clearly it showed up. Then we can investigate all these ports. And in some cases, like Wireshark would tell us like, hey, something is like definitely wrong. So for example, here, I think I configured my Wireshark to start doing this, but like it's telling us, for example, the checksum is correct. Don't remember how I did that. Let's see here. Reference edit preferences, protocols. So this is also like a hint for level 14 again. So I know a lot of people are having fun with level 14. Validate the TCP checksum if possible. Normally that's off. I turned it on. And now we can see like Wireshark is telling us like, hey, this checksum is correct, for example. Not super important for this level, but that's just kind of a hint for level 14. But that's the basic idea is we're sending these packets, and if something is going wrong, aka in this case, like you're not getting the flag, run it with sudo practice mode and look at these PCAPs and see what packets are showing up and what the fields are with Wireshark, that everything looks like how you're expecting it to look. Okay, any final questions about levels 9 or 10? Nope, okay. Are there any questions about, let's say, everything before level 14? Yeah. 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 You can use Scapy to do that. The simplest way, like you said, is definitely to use Wireshark or use TCP dump and just like see that packet. So let's actually look at that. So level 11. So I guess level 12 must be the ARP one then. Level 11. Okay. So we do sudo challenge baby intercept. And we do, it's telling us in this challenge, you will manually perform a TCP handshake. The initial packet should have this set up. So there's kind of a field omitted, right? The flags field is also critical as part of the TCP handshake, but hopefully you can infer that from the fact that you're doing a TCP handshake. The handshake should occur with the remote host at 10.0.0.3. So again, for those unfamiliar, if we look at this video on TCP, it shows us the TCP handshake. So we want to send like hello world from host A to host B. This TCP handshake is sending a SYN packet with some sequence number, sending the host B responds with a SYN ACK packet, and then host A responds with an ACK packet. This right here is the TCP handshake. The critical detail to note is this sequence number starts at some random value. In this case, we're just calling that random value A. The host responds with its own random value B and increments A by 1 as its acknowledgement number. And you now need to reply with sequence number of A plus 1, kind of one more than your initial value, and then also acknowledge one more than its sequence number. This is kind of this handshake of establishing these sequence numbers at the beginning of a TCP connection. So if we want to do that with Scapy, let's see here, tmux. And in this case, we're not going to use the practice mode PCAP, so we're just going to manually TCP dump on ETH0. So we're just looking at live traffic. And yeah, let's just do that. So now if we do, for example, Scapy send P, and we create this whole setup of Ethernet IP TCP, where we do iface equals ETH0. We want our source to be get hardware adder ETH0, get IF hardware adder. that just sent out that packet. We can see that this packet just went out. In this case, it's got a lot of empty stuff, but obviously we can start filling that in. We want an IP address from IP equals 10.0, or source, sorry, it has source equals 10.0.02, destination equals 10.0.0.3. Right now we've got this filled in correctly, and then on top of that we have ports within the TCP layer. And we can do, for example, dport equals 31337, and source port equals 31337. And now we've almost got this filled in correctly. In the case of this challenge, it's operating a little non-standard to what would actually be functioning from within the kernel's perspective, because the challenge is automatically sending you your SYNAC back. It's waiting for all of these fields to be correct. So the challenge told us we need a source port of 31337, a destination port of 31337, and also a sequence number of 31337. Only under these circumstances is it going to respond with a SYNAC, which is non-standard. Normally you get a SYNAC either way, but this is how the challenge is designed. Yeah, so now we can see right here, if we clear this, re-show everything, send this packet out, we can see there's two packets, right? So we've got 10.0.0.2 talking to 10.0.0.3. It's got this SYN packet, and then 3 responds to 2 with a SYNAC packet. And as you pointed out, there's this sequence number here coming from 10.0.0.3 that we need to be ready to acknowledge and add 1 to, right? Because if we look back here, we said that host B is going to respond with sequence equal to some random number and acknowledgement equal to a plus 1. So we can see it's acknowledging us, right? We sent a sequence number of 31337. It's acknowledging 31338. So we need to get ready to add 1 to this as our acknowledgement number and use this as our sequence number. So as you pointed out, we could just finish this out by using TCP dump and just manually copy over this number. Alternatively, we've got this other function within SCAPI, which instead of using send p, we can do sr1. And is that true? No, srp1, I think. Yes, srp1. And what srp1 is it means send and receive packets at layer 2 and return only the first answer. So basically, it's going to send a packet, it's going to receive 1 packet. That's what srp1 means, basically. So we can use that to collect this number instead to kind of programmatically do this. So if we do this, we can see that we're getting this packet back where it's got this sequence number that's random and an acknowledgement number of 1 more than 31337. Right, every time we run this, we're going to get a different sequence number. And this is our SYNAC packet coming back. So if we say response equals this, and then we say like response, actually, what is the type of response? Yeah, so we can do like response TCP sequence number. And this, in the same way, right, we can see here, this starts with 412. This gives us 412. So we can do something like this. And in this case, I'm just going to print response TCP sequence, right? So every time I do this, I'm getting my sequence number back. So this is how you can use SCAPI to automatically collect that final packet. If you don't want to use TCP dump and just kind of like copy this over, you want to do things programmatically, SRP1 is how you do that. Okay. Any more questions on levels before level 14? Yeah. Level 13. Okay. So we're going to run it in practice mode just in case. Okay. Cool. So level 13, if we run the challenge, is going to tell us, in this challenge, you will hijack traffic from a remote host. You do not have the capabilities of a net admin. the remote host at 10.0.0.4 is communicating with the remote host at 10.0.0.2 on port 31337. So in this case, since we're running the challenge in practice mode, we can confirm that this is actually happening. So normally if I just run TCP dump I 80, we're not going to see any traffic happening. Nothing cool is happening except this random IPv6 stuff. But there's no cool traffic happening. On the other hand, if we do TCP dump and use the fact that we're running this in practice mode with sudo, we could confirm that stuff is in fact happening. Run reset real quick. And if we do TCP dump -l-r, and we'll even do with -xx, and temp pcaps IP 10.0.0.2, we look at this, we can see, I mean, at some point the flag is being communicated over here. Obviously, we're using practice mode. You're not going to get the real flag using this methodology, but we can use practice mode to understand what's going on the network. And we can see, let's pick this to less. We can see that we have some, where did that go? What? Okay. We can see that we have, if I scroll, is it going to let me scroll? Why is it not letting me scroll? To temp/data less temp data. Cool. So we can see that we have this SYN packet. Why is it so confused? Whatever. We can see that we have this SYN packet, we have this SYN ACK packet, we have this ACK packet, right? This is our three-way handshake. And then we have some data get pushed to us, which is the flag. So 10.0.0.4 is telling 10.0.0.2 the flag. And it's telling us that in this challenge, our goal is to hijack that traffic, which makes sense, right? Because 10.0.0.4 is sending the flag to 10.0.0.2. If we can hijack that traffic, we can see the flag. That seems pretty cool. We did this similar concept in a previous level. However, we had the capabilities of a net admin, which allowed us to add an IP address to this interface. But that's not going to work for this challenge. So if we look at this, the remote host at 10.0.0.4 is communicating with the remote host at 10.0.0.2 on port 31337. We want to become or we want to see this traffic somehow. And in the previous level, on level 12, you looked at this concept, and we demonstrated it in the previous Q&A, that we can just send an ARP reply whenever we feel like it to a host, and it's going to update its ARP caches and think that's where that IP address is. So a little more explanation on that. We have this concept here. Notes.txt. Cool. Wait, why is that not working? Oh, I ran the challenge with sudo. Let's just write this out. Okay. So we have this concept of, actually one more thing. Let's see. Let me run the challenge one more time and show one more important concept of what's going on, which is TCP dump this from 10.0.0.4. Let's look at this one more time. Okay, there's one other thing that's happening, which is, why is this being weird? Let's filter this just for ARP. Wait, why are we not seeing the ARP? Let's see here, 10.0.0.2, no. We run the challenge one more time. We might be missing it because when it starts listening, we might have missed it. Okay, but here's what's happening. Let me just explain what's happening here. Notes.txt. Okay, so what's going to happen is that the goal of 10.0.0.4 is to talk to 10.0.0.2, and it's going to communicate the flag. So its goal is to say, we'll say flag, right? 10.0.0.4 is sending the flag to 10.0.0.2. This is what's happening on the network as we showed before. In order for this to happen, a number of steps need to happen. So if 10.0.0.4 wants to talk to 10.0.0.2, it needs to figure out 10.0.0.2's MAC address because it needs to send an Ethernet frame, an Ethernet packet, in order to even reach 10.0.0.2, right? As we've previously discussed, Ethernet is the first layer because in order to even physically send this packet, we need an Ethernet packet that is kind of like the physical link layer. It's actually sending data, which on top of it's going to be IP, on top of that's going to be TCP, etc. So we don't know initially what 10.0.0.2's MAC address is. All we know is that we want to talk to 10.0.0.2. So what 10.0.0.4 is going to do is it's going to broadcast, and it's going to say who has 10.0.0.2. We'll even say this a little more normally, or like nor what it looks like within TCP dump, for example. Who has 10.0.0.2 says 10.0.0.4. This is what's going to be broadcasted. So everyone physically linked in is going to receive this packet at the very beginning. We didn't see it because when it starts capturing is a little bit too late. But this packet is in fact being sent. It says 10.0.0.2, who has 10.0.0.2 says 10.0.0.4, because we need to start talking on the link layer to 10.0.0.2. And 10.0.0.2 is an IP concept. It's not a link concept. Link concept means MAC address. We need the MAC address of 10.0.0.2. So this is going to happen. And now what's going to happen is that 10.0.0.2 is going to say is or 10.0.0.2 is at, and then we'll come up with a random MAC address, says, I guess we don't need to, what does that normally look like? 10.0.0.2 is at, yeah, we'll just say this. And that's going to be sent back to, and actually before we do this, let's say ETH0 of IP 10.0.0.4. We're going to say, how do I want to write this? We'll say this. We have a bunch of interfaces. So we'll say we have 10.0.0.4, which has some random MAC address. We'll say it's 112233445566. We have another interface, so that we'll say that this is host IP 10.0.0.4. So this is some host on our network. We have another host on our network, which is 10.0.0.2. So it has an IP address of 10.0.0.2, and we'll say it has this MAC address. And then we also have ourselves on this network, and we'll say that we are 10.0.0.3, and we have, let's say, 1A, 2B, 3C, 4D, 5E, 6F. This is our MAC address, right? So we have 3 IP addresses, 3 MAC addresses, 3 hosts. This is what's going on the network. Okay, so this happens. This is what we're trying to do. Goal is this, right? And in fact, we know that this is happening. We show that this is happening. How? This is how this happens. So we need to figure out the MAC address. We broadcast the who has, and then 10.0.0.2 responds because it says, oh, this packet just came into me. The kernel says, hey, this packet just came to this interface. And guess what? My IP address is 10.0.0.2. Well, my MAC address is this. So let me send out a response saying 10.0.0.2 is at our MAC address of AABB, etc. So this also, we now know, because we know who sent this to us. The source information is embedded within this. So this only goes to 10.0.0.4, let's say. Or, yeah, we'll speak on the IP layer for now, for who we're talking to. But this is what happens, right? This is our ARP request and our ARP reply. So now we know who we're talking to. So now we can do 10.0.0.4, can do a SYN packet. Let's see there, to 10.0.0.4, 10.0.0.2. 10.0.0.2 responds with a SYN-ACK packet to 10.0.0.4. 10.0.0.2 replies with an acknowledgement packet to 10.0.0.4. Whoops, we got that backwards. 4, 2, right? So 4 talks to 2, 2 talks to 4, 4 talks to 2. This is our 3-way TCP handshake. And now finally, we can do flag. Right? This is everything that needed to happen. So we have these 6 packets that had to happen in order for all of this to work. Okay, there is an important step though, which is how do we know the MAC address when we go to do this, to establish this TCP handshake with 10.0.0.2? How do we know the correct MAC address to send this packet to? How do we know that? Well, we know that because we just did this request, but these events are entirely independent of each other. This like network traffic is completely isolated from this network traffic. They're like not, I mean, we can say they're related, but they're not really related. They're just completely separate packets. What really needs to happen here is we have an ARP cache that gets updated. And now when we did this, we know for the next 60 seconds starting now, is that 10.0.0.2 is at this right here. So we have this ARP cache. And now when we want to do any IP traffic, and we know that it's on our local network, we can correctly formulate these Ethernet packets because we have our ARP cache that is storing this MAC address. And now we can send this packet correctly. After 60 seconds, if we want to send it again 60 seconds later, we're going to see that we've got to do this again because our cache is no longer holding it. We're going to do a who has request again, and it's going to last for 60 seconds. But that is how this is known. The question, though, is, I guess, what causes this cache to be updated? Well, what causes this cache to be updated is whenever we receive a response of an ARP response saying is at. Whenever we get this packet right here, the kernel is updating our ARP cache on this networking device. It's just updating our ARP cache. So whenever we get an is at packet, the cache gets updated. So if we just randomly send, let's say, let's modify this packet. We randomly send this packet right here, let's say from 10.0.0.3 ourselves, and we'll just say, hey, 10.0.0.3 is at, and we'll just make something up. It doesn't even matter, right? 3, 4, 5, 6. Notice this isn't even us, right? We said before that 10.0.0.3 is this MAC address, and we just sent a random thing. We're saying we're right here. Why you would do this? I mean, the kernel's not going to do this itself, but we have the ability to inject raw packets, and so there's no reason we couldn't communicate this. Well, as soon as 10.0.0.4 gets this, it's immediately going to do the exact same thing. ARP cache starting now. And let's say there's, I don't know, at this point, let's say there's 40 seconds remaining on this one. And now we'll say 60 seconds starting now that 10.0.0.3 is at here. As soon as it receives this is at packet, ARP cache gets updated immediately. And now if 10.0.0.4 ever tries to talk to 10.0.0.3, it's going to use this as the destination MAC address. But again, this is completely just made up. We just randomly injected this packet into the network. We could also inject, let's say 777 is at of all of this as well. And now ARP cache immediately gets updated. And we'll say 60 seconds starting now. This IP address right here is at there, right? We can just send this is at packet and the ARP cache gets updated. So now if it was to ever talk to 777, it would go over that MAC address. All of this to say that if we now do 10.0.0.2, we pretend to be someone else on our local network that 10.0.0.4 really cares about, and we say this, well, guess what? This cache entry gets invalidated because we're talking about 10.0.0.2 and we have new information on 10.0.0.2. And now we have this. Oops. We get this updated. And we'll say 60 seconds starting now or whatever, right? Starting now. Okay, so we just updated 10.0.0.2. Again, conceptually, like if we think about this in quote unquote correct terms, 10.0.0.3 is the one that sent this. But 10.0.0.4 has no clue what to trust other than what this protocol dictates it should be doing. And it received a packet saying 10.0.0.2 is over here. And so it's going to update its ARP cache. And now if it wants to start talking to 10.0.0.2, this is going to be the destination MAC address. And of course, if instead we do this, right? Nope. We do this. And we send this packet instead. We say 10.0.0.2 is here, instead of this just like completely made up MAC address. we say this, now this gets updated here. And if 10.0.0.4 ever wants to talk to 10.0.0.2, it's going to talk to it over this destination MAC address. And the thing to note here, right, of critical importance, three is MAC address, right? We just tricked it. This is really 10.0.0.3's MAC address, but we told it, hey, this is 10.0.0.2's MAC address. So now we're going to be hijacking this network traffic. So if we want to see that in demonstration, let's run the challenge. And if we do tmux, if we do, let's create one more window. Again, if we do xxl-r temp pcaps 10.0.0.2 or IP 10.0.0.2's data, right? We can see that the flag is being communicated right here, right? You can see that's happening. That's nowhere to be found in 3's information. We just have all this lame IPv6 stuff happening. Nothing cool is happening though on 10.0.0.3. On 10.0.0.4, we can see the flag also because, or I guess I had some things backwards, right? 10.0.0.2 is telling the flag to 10.0.0.4. That's the direction that's happening. But we can see the flag on both sides of 10.0.0.2 and 10.0.0.4. But we can see, right, 10.0.0.2 is sending the flag to 10.0.0.4. And we can see that from both sides. Yeah. So 2 is telling 4 the flag. 3 has no ability to see this because it's not a recipient of this traffic. This traffic isn't going over the broadcast MAC address. It's not showing up. But what we can do is we can tell 10.0.0.2 where 10.0.0.4 really is. Where really is we're just going to make up a new location. So so this is 10.0.2, it's traffic, and let's do while true, do tail c plus 0 dash f temp pcaps IP 10.0.0.2, pipe that into TCP dump L or XX dash L dash R standard input, done. Okay, so now we're seeing the packets as they come. So we can see, are we seeing that? I don't remember how often these packets get sent. Or are we not seeing that? Client host. Actually, why are we not seeing new packets? Are we running this in sudo? Are we looking at old data? Hold on. Let's make sure we're running this correctly. Yep, so we didn't run it with sudo. We had old traffic there. Okay, sudo with this. And tmux. Oops. rm tmux 0. Run the challenge again. Okay. tmux, create a new window, while true, do tail-f-c plus 0 temp pcaps IP 10.0.0.2, pipe that into TCP dump xxlr dash done. Boom. Okay, so we're getting all of these packets as it's coming in. So 10.0.0.2 is telling the flag to 10.0.0.4. It looks like that's actually happening in both directions. So the service that's actually running here, so if we netcat to 10.0.0.2, 31337, it's just echoing everything we say to it. So that's what's going on there. That's why 2 is also saying the flag to 4. Is that 4 is initially telling the flag to 2. Okay, so we can see, let's actually look real quick. Yeah, so 4 initially, if we look at this, right, we have our SYN ACK, we have an ACK, and then the very first time it gets pushed is from 4 to 2, sending the flag, and then it's just repeating it back. So if we tell 4 where 2 can be found, so we can see this right now. If we do this, send packet ARP destination, broadcast this out, 4, 5, 6. Source equals get IF hardware adder ETH0. Oops, that is not an ARP packet, that is an Ether packet. Put an ARP packet on top of this. And we say op equals is at. Our hardware source equals, how do we want to write this? Source equals AA, BB, CC, DD, EE, FF. Destination, now we'll do that. So hardware source is this source. Key source, so our hardware source is this made up thing. Our protocol source is, let's say, 10.0.0.2. And then our hardware destination equals, how do we want to do this? Well, let's do one more thing. Let's do an ARP ping to 10.0.0.4. So we can do this, and if we run arp-n, actually that doesn't update our ARP cache. Great. If we do this ARP ping of 10.0.0.4, we can see 10.0.0.4's MAC address, so let's copy that to correctly formulate this packet. P source equals this, hardware to hardware source equal, or hardware destination equals this, and key destination, protocol destination equals 10.0.0.4. Okay, so we're telling 10.0.0.4 on its correct MAC address. Actually, we'll also do, we'll just only tell 10.0.0.4. 3A, DA, 9C, 64, 9B, 40. So we're going to tell 10.0.0.4's MAC address that from us is at hardware source. So we've just kind of made up a hardware source. We're saying that our protocol source is 10.0.0.2. So we're telling it where 10.0.0.2 can be found at. And we're sending this to 10.0.0.4 correctly. So if we run this and send it, iface equals ETH0. When we now look at this, yeah, so see, it's panicking now. See, it's only sending SYN flags because look, 10.0.0.4 is talking to 10.0.0.2. This is all at the IP layer when we're looking at this in TCP dump. But if we actually look at these packets, right, the beginning of this right here, this is the destination MAC address. So it's sending it to this MAC address, which is a completely made up MAC address. So it's not actually arriving physically to anyone. It's just sending this out to AA, BB, CC, DD, EE, FF. And all it can do is send these SYN packets. It's trying desperately to connect to 10.0.0.2, but 10.0.0.2 isn't getting these packets because it has an incorrect MAC address. So this is just going to no one. And that's why we're not seeing a SYN ACK at some point on 10.0.0.4's perspective, is it just keeps sending out the SYN packet, waiting for it to SYN ACK back, but it's never going to happen. Not entirely true. It's now working. And the reason for that is that eventually, and I don't know why it happened so quickly, but eventually we got another is-at packet that is now correctly telling it where 10.0.0.2 is. So see, now it has this, let's see here. See how it now has this? This is 10.0.0.2's real MAC address. So we watch this, right? It's correctly communicating, the flag is going, blah, 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 blah. We resend this packet that we sent before again, it's going to get cut off. So it is now no longer talking correctly to 10.0.0.2. You're not seeing the flag in this traffic. All we're seeing is a bunch of SYN packets. It's desperately trying to connect. It's failing to do so, though, because it's not talking to the correct person. We've updated its ARP cache, and now 10.0.0.4 is just like unable to communicate with 10.0.0.2 because it thinks this is its MAC address. Again, if we set this now instead to be, let's say 42, 42, 42, 42, 42, 42. Now it is going to be talking to, well, it's timed out right now because of the way TCP works. It only tries so many attempts to connect, and then it kind of gives up for a while. and then eventually it'll start trying to talk to it again. Not sure how long that's going to take. There's a whole protocol of like basically TCP doesn't want to just keep sending packets that are never arriving. So it has this like back off period where it's like, okay, clearly no one's talking to me, so I'm going to back off. Okay, now we just got another one. We can see it's not coming very quick. Oh, but we just had an ARP request who has 10.0.0.2, tell 10.0.0.4, and who has 10.0.0.2, tell 10.0.0.4. It's sent this out only to this MAC address. It needs to broadcast this who has request though in order to be correctly updated, which probably eventually it will. So whatever's happening right now is the network driver that automatically sends packets is like panicking and trying to recover. So I guess its first step is to just start like basically ARP pinging 10.0.0.2 and be like, hey, are you there? Are you there or not? Like, tell me if you're there. And of course, it's going to this destination MAC address, so it's not getting replies. Eventually, what I would expect to see is eventually it'll broadcast out a who has request again. It might take a minute before it does that. But that's what we're watching happen right now is the networking driver that automatically is sending a bunch of packets. And okay, I guess somehow we missed it, but now it has somehow figured out the correct destination and they're correctly talking and the flag is going out again. Again, we can do this again and it just totally disrupts everything, right? But if we set this to ourselves, right, instead, we're going to start getting this traffic. Yeah, so now it's correctly talking. The flag is being communicated. Part of what's going on is our host is automatically forwarding that correctly to 10.0.0.2. But if we were to, for example, TCP dump I ETH0, which you can do without practice mode, right? We would see all of this conversation happening. And if we add that -XX, we would see the flag showing up over here. So that's the whole idea of ARP poisoning, is to just tell the host where a MAC or where an IP address can be found. And then it's just going to automatically follow the protocol. It's going to update its ARP cache, and it's just going to start sending things meant for 10.0.0.4 or to getting these IP addresses mixed up, but it's just going to update the link of a MAC address to an IP address and just start using that because it has no reason to believe that someone would lie to it. It's just assuming what you're saying is true, that it is at there, and that is what is happening there. Okay, any more questions about level 13 and this concept of like ARP poisoning? Nope. Okay, cool. There's a question about 14. We're kind of out of time. I briefly discussed 14 in the previous office hours, but something to know about level 14 is it's basically going to be the same thing. We'll just quickly launch it to look at the description. It's basically going to be one more step of 13, which is to take things one step further and to start inserting traffic in as well. So we just saw how we can hijack traffic to just start passively watching it. This challenge takes it one step further, which is to just start also talking to 10.0.0.3. So we showed how we could watch 10.0.0.4 and 10.0.0.3 talk to each other. Well, what happens if in the middle of that, you start sending TCP packets also talking to 10.0.0.3? You can start inserting traffic in, and it has no way of distinguishing it. So that's what level 14 is going to have you doing, is not only passively watching this, but actually inserting traffic into the network to add an interaction, basically. If there's more questions on that, though, feel free to ask on the Discord. I will look into the possibility of, again, extending the deadline through maybe Sunday. Not confirming that yet, but I will update everyone tonight if the assignment is extended through to Sunday or not. Probably will be, but wait till the confirmation. And that is all. Thank you, everyone, for coming to class. Oh, there's one more question. Yeah. Hold on, let me check real quick. Who made the announcement? Yeah, I think Donkey is doing an extra office hours, and that would be for this class. Yeah. Yep. Yep. That's everything. Okay. Yep. See ya.